Welcome to my YouTube channel, Usano-Goldie RL Marquez. This is Integral Calculus or Calculus 2, Basic Integration, Section 1.4, Exponential Formulas for Integration. In this video, I'm going to discuss indefinite integrals that can be handled by exponential formulas for integration. In the previous videos, I discussed the general power formula and the logarithmic formula for integration. This time, I'm going to discuss another basic integration formulas. These are exponential formulas for integration. Let u be a differentiable function of x. Then, the integral of a to the u du is equal to a to the u over ln a plus c, where a is greater than 0 but not equal to 1. If a happens to be e, which is approximately equal to 2.71828, then this integral of e to the u du becomes integral of e to the u du equals e to the u plus c. In the integral a to the u du, a to the u is the power function not equal to a constant. A is the base, which is a positive constant different from 1. U is the exponent, which is a function other than a constant. And du is the differential of the exponent u. If all of these requirements are satisfied, then the integral of a to the u du is equal to a to the u over ln a plus c. Remember, a is greater than 0 but not equal to 1. Let us have the following examples. Example 1.4.1. Evaluate the integral of 2 to the 5x plus 3 dx. Solution. Here, we take a equals 2. Its exponent as u, which is equal to 5x plus 3. Let's take the differential of u. It gives us 5 dx. But this differential du, which is equal to 5 dx, is not present in the given integral. There is a missing constant factor 5. Let us apply the 5 and then balance outside by 1/5. This integral now takes the form of integral of e to the u du. Hence, 1/5 integral of 2 to the 5x plus 3 times 5 dx is equal to 1/5 times 2 to the 5x plus 3 over ln 2 plus c, or 2 to the 5x plus 3 over ln 32 plus c. Example 1.4.2. Evaluate the integral of pi to the 2x to the 5th times x to the 4th dx. Solution. Given the integral of pi raised to 2x to the 5th times x to the 4th dx, a here is equal to pi, u is equal to 2x to the 5th, du is equal to 10x to the 4th dx. This is not exactly present in the given integral. There is a constant factor missing, which is equal to 10. Let us apply that inside and then balance outside by 1 over 10. This integral now takes the form of integral of a to the u du. Hence, we have 1 over 10 integral of pi raised to 2x to the 5th times 10x to the 4th dx is equal to 1 over 10 times pi raised to 2x to the 5th over ln pi plus c, or pi raised to 2x to the fifth over 10 ln pi plus c. Let us have another example. Evaluate the integral of 10 to the cosine 3 theta sine 3 theta d theta. Solution. Given the integral of 10 to the cosine 3 theta times sine 3 theta d theta, a here is equal to 10, u is equal to cosine 3 theta, du is equal to derivative of cosine 3 theta is negative 3 sine 3 theta multiplied by d theta to be du. Checking the integral, there is a constant factor negative 3 that is missing for this to be du. Let's supply that negative 3 inside to complete the du, then balance outside by negative 1/3. This integral now takes the form of integral of a to the u du. Hence, we have negative 1/3 times 10 to the cosine 3 theta over ln 10 plus c, or negative 10 to the cosine 3 theta over 3 ln 10 plus c. Example 1.4.4. Evaluate the integral of e to the tangent 2y secant squared 2y dy. Solution. Given the integral of e to the tangent 2y secant squared 2y dy, here u is equal to tangent 2y. Taking its differential, we have 2 secant squared 2y dy. This differential is not exactly the differential present in the integral. So there is a constant factor 2 that is missing. Let's supply that constant factor 2 inside and then balance outside by 1/2. This integral now takes the form of integral of e to the u du. Hence, we have 1/2 e to the u plus c, but u is tangent 2y. Example 1.4.5. Evaluate the integral of 3 to the square root of 3y to the fourth plus 2 multiplied by y cubed dy over square root of 3y to the fourth plus 2. Solution. Given the integral of 3 raised to square root of 3y to the fourth plus 2 multiplied by y cubed dy over square root of 3y to the fourth plus 2, we can write this as integral of 3 raised to square root of 3y to the fourth plus 2 times y cubed dy over square root of 3y to the fourth plus 2. Here, a is equal to 3, u is equal to square root of 3y to the fourth plus 2. Let's check if y cubed dy over square root of 3y to the fourth plus 2 is its differential. Taking the differential of u, we have derivative of 3y to the fourth plus 2, that is 12y cubed, over 2 is square root of 3y to the fourth plus 2 multiplied by dy. Simplifying, we get 6y cubed dy over square root of 3y to the fourth plus 2. So for this to be the differential of u, we need a constant factor 6. So let us apply that inside and then balance outside by 1 over 6. So this integral now takes the form of integral of a to the u du. Hence, we have 1 over 6 times 3 to the u over ln 3 plus c. So that is 3 to the square root of 3y to the fourth plus 2 over 6 ln 3 plus c. Example 1.4.6. Evaluate the integral of x to the 6 e raised to log of 1 minus x to the 7 dx over 1 minus x to the 7. Solution. Given the integral of x to the 6 e to the log of 1 minus x to the 7 dx over 1 minus x to the 7, we can write this as integral of e to the log of 1 minus x to the 7 multiplied by x to the 6 dx over 1 minus x to the 7. Here, our u is log of 1 minus x to the 7. Taking its differential, we have derivative of the argument of log, that is negative 7x to the 6 over 1 minus x to the 7 times ln 10, then multiplied by dx. So this differential of u is not exactly in the given integral. We need a constant factor, negative 7. So let us supply that inside together with ln 10 in the denominator. Balance outside by negative ln 10 over 7. This now takes the form of integral of e to the u du. Hence, we have negative ln 10 over 7 times e to the log of 1 minus x to the 7 plus c. Example 1.4.7. Evaluate the integral of e to the tangent inverse of y squared multiplied by y dy over 1 plus y to the fourth multiplied by pi raised to tangent inverse of y squared. Solution. Given the integral of e to the tangent inverse of y squared y dy over 1 plus y to the fourth times pi to the tangent inverse y squared, we can express this as e over pi raised to tangent inverse of y squared multiplied by y dy over 1 plus y to the fourth. Here, our a is e over pi. U is equal to tangent inverse y squared. Du is equal to derivative of y squared 2y over, for inverse tangent, over 1 plus y to the fourth times dy. For this to be du, y dy over 1 plus y to the fourth, we need a constant factor 2. Let's supply that. Balance outside by 1/2. This integral now takes the form of integral of a to the u du. So hence we have 1/2 integral of a to the u du, and that is equal to 1/2 times a to the u over ln a plus c, or that is e over pi raised to, our u is inverse tangent y squared over 2 ln of e over pi plus c. Example 1.4.8. Evaluate the integral e raised to 3 cosecant inverse of 5 ln x dx over x ln x is square root of 25 ln squared x minus 1. Solution. Given the integral of e raised to 3 cosecant inverse of 5 ln x dx over x ln x is square root of 25 ln squared x minus 1. Let us express this in the form of integral of e to the u du. So hence we have integral of e to the 3 cosecant inverse of 5 ln x times the possible differential, which is dx over x ln x is square root of 25 ln squared x minus 1. So here we take u equals 3 cosecant inverse of 5 ln x. Getting its du, we have 3 times negative. For the derivative of 5 ln x, we have 5 over x. Then, since this is cosecant inverse, we have over 5 ln x is square root of 25 ln squared x minus 1, and that is negative. So getting negative 3 dx over x ln x square root of 25 ln squared x minus 1. Checking the differential inside the integral, so there is a missing constant factor negative 3. So let's apply that. Balance outside by negative 1/3. So this integral now takes the form of integral of e to the u, and then this is du. Hence, we have negative 1/3 e to the u. U is 3 cosecant inverse of 5 ln x, then plus c. So let us have this last one. Evaluate the integral of e raised to e to the cotangent inverse of 3w plus cotangent inverse of 3w all over 1 plus 9w squared dw. In this integral, let's rewrite it in the form of integral of e to the u du. Hence, we have integral of e to the cotangent inverse of 3w times e to the cotangent inverse of 3w times dw over 1 plus 9w squared. Possible u here is the exponent of e, and that is e to the cotangent inverse of 3w. Its differential is given by e to the cotangent inverse of 3w times, for the derivative of cotangent inverse 3w, that is negative 3 over 1 plus 9w squared multiplied by dw to be its differential of u. Let us apply simple u substitution. Solving for negative d over 3, we get e to the cotangent inverse 3w dw over 1 plus 9w squared. So hence we have integral of e to the u times, so this expression is negative d over 3. And this integral is equal to negative 1/3 integral of e to the u du. And integral of e to the u du is equal to e to the u plus c. So hence we have negative 1/3 e to the u plus c. But u is equal to e to the cotangent inverse of 3w. Hence we have negative 1/3 e to the cotangent inverse 3w plus c. For your practice exercises, we have the following 8 integrals that you can work on. Thank you for watching.